everyone, my name is Iman and I did my degree in medical biophysics, and today I'm going to walk through fluid flow and specifically how to think through these questions on the MCAT without relying on memorizing a bunch of equations. A lot of people find this topic pretty confusing at first, I know I did, but once you really understand the relationships, it actually becomes very predictable. By the end of this, you should feel comfortable figuring out how velocity changes when area changes, how pressure reacts using Bernoulli's principle, and then applying both of those ideas to solve MCAT-style questions. So the goal here is not just to go over formulas, but to make the reasoning behind them feel very intuitive. If you've seen fluids before, it can feel like there are a lot of equations and not a lot of guidance on how to use them. And on the MCAT especially, questions are often set up in a way where memorizing doesn't really help. You actually have to really reason through what's happening. So instead of focusing on equations first, we're going to focus on what's changing in the system. The first idea we need is continuity. All this is saying is what flows stays constant. Whatever goes in has to come out. So if the pipe becomes narrower, so the area decreases, the fluid can't just disappear, it must move faster to keep up. I like to think of it like traffic. Same number of cars, smaller road. They have to move faster or pack closer together. So from this, we get that when an area decreases, velocity increases, and when area increases, velocity decreases. The second key idea is Bernoulli's principle, which is basically energy conservation but applied to fluids. So pressure, motion, and height are all connected. If one increases, something else must decrease. The main takeaway for the MCAT is that if velocity increases, pressure decreases, assuming height that stays the same. Another way to think about it is that the energy is being redistributed. If more energy goes into motion, less is available as pressure. If we look at the equation here, we've got the pressure, the motion, and the height component, and so the number on the left-hand side of the equation must be the exact same as the right side. So if something on the left hand increases, something on the right side must decrease to ensure that we have continuity in our equation. When we combine these two ideas, we get what's called the Venturi effect. In a narrower section of a pipe, velocity increases and pressure decreases. This is a really common pattern on the MCAT. So if you remember one thing, it's just narrow leads to fast and fast leads to low pressure. So here's how I would actually approach these questions. Instead of jumping into equations right away, I'd start by asking what is changing, is the area changing, is the height changing, and then we would identify what equations we would need to use then. Let's try a quick concept check question. Question 1. A pipe narrows. What happens to velocity? When a pipe narrows, the cross-sectional area decreases. From the continuity equation, area 1 velocity 1 equals area 2 velocity 2. If the area goes down, velocity has to go up to keep flow rate constant. The same amount of fluid still has to pass through the pipe each second, so it moves faster in the narrow region. So if you selected that velocity will increase, you would be correct. Let's try concept check question number 2. A pipe narrows. What happens to pressure? Pressure decreases. Once the pipe narrows, velocity increases. According to Bernoulli's principle, when velocity increases, pressure decreases if the height stays the same. That is because more of the fluid's energy is going into motion, so less is available as pressure. We can think of it as a narrower area leads to faster flow and lower pressure. Concept check number 3. If a fluid flows faster, what must happen to the pressure if it remains at the same height? And if you said the answer was decreases, then you would be correct. This is testing the same Bernoulli idea more directly. If the fluid flows faster and the height remains unchanged, then the increase in velocity term means the pressure term must decrease so the total energy stays constant. So at the same height, velocity increases but pressure decreases. Let's move on to a more application-style MCAT problem. This one combines changes in velocity and height, so it's a little bit more involved. And yeah, let's take a quick look. So, an office building with a bathroom 40 meters above the ground has its water supply enter the building at ground level through a pipe with an inner diameter of 4 centimeters. If the linear speed at the ground floor is 2 meters per second and at the bathroom is 8 meters per second, determine the cross-sectional area of the pipe in the bathroom. If the pressure in the bathroom is 3 times 10 to the 5 pascals, what is the required pressure at ground level? So this question is testing a couple different concepts, but let's walk through it. I like to break down more complicated questions like this into multiple steps so it makes it easier to solve and reason through. So my first step would be to identify the concepts that are being tested in this question. I can see that we have a changing in area and changing in velocity, so I know that we're going to have a continuity equation, and I also see that we're relating pressure, velocity, and height, so I know we're going to be using Bernoulli's equation. So step 2, let's start with continuity. We use the equation A1V1 equals A2V2, and which tells us that flow rate stays constant. First, I want to solve for the unknown area A2, so I rearrange the equation to show that A2 equals A1V1 over V2. Now I substitute in the known values. The original pipe has a diameter of 4 centimeters, so the radius is 2 centimeters, or 2 times 10 to the negative 2 meters. Don't forget to convert your units into proper standard units, or else this would mess up our calculations and overall our answer to the question. Then I multiply by the initial velocity, which is 2 meters per second, and divide by the final velocity of 8 meters per second. After simplifying, we get area equals 3.14 times 10 to the negative 4 meters squared. So the area at the bathroom level is much smaller, which matches our expectation since velocity increased. Next, we apply Bernoulli's equation to find the pressure at ground level. We use the full form of Bernoulli between 2 points. Then we rearrange to solve for P1, the pressure at ground level. Now we substitute in our given values. We're given that pressure at the top is 3 times 10 to the 5 pascals, the density of water is 1,000 kilograms per meters cubed, and gravity is 9.8 meters per second squared. The velocity increases from 2 to 8 meters per second, and the height difference is 40 meters. So plugging everything in, we get P1 equals P2 plus all of this density times this entire term over here. Then we simplify step by step. We evaluate the velocity term first and then the height term. The velocity contribution comes from the difference in squared speeds, and the height term comes from the 40-meter increase. After calculating both contributions and multiplying by density, we add that to the pressure at the top, and then we approximately get P1 equals 7.3 times 10 to the 5 pascals. So to wrap everything up, instead of memorizing equations, focus on what's changing and how the variables are related. Use continuity to understand velocity, and Bernoulli to understand pressure, and connect the two when needed. That approach will make fluid questions much more manageable on the MCAT. Thank you for listening, and have a good night.